Practices webinar series, which is brought to you by the IDEAS Productivity Project with funds from the Exascale Computing Project. The series is also a collaboration involving the U.S. Department of Energy computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Labs. I'm Mosley Marquez from Lawrence Berkeley. Ashley from Oak Ridge and I will be the hosts for today's webinar, Best Practices for Using Proxy Applications as Benchmarks. The webinar will be presented by David Richards from Lawrence Livermore and Joe Glensky from HPE. David is a computational physicist at the Center for the Applied Scientific Computing at Lawrence Livermore. He leads the Advanced Architecture and Portability Specialists team there, and he's also the PI for the Proxy Apps project with funds from the Exascale Computing Project as well. David has won a Gordon Bell Award in 2007 and also a R&D 100 Award in 2013. He holds a PhD in physics from the University of Illinois at Urbana-Champaign. Joe is an expert on high-performance computing architectures and performance with a deep understanding of the ways HPC systems advance science. He had led technical work for HP, Cray, and SGI for major procurements, critical system acceptances, and new product bring up. He guides the performance and benchmark activities for the Frontier system at Oak Ridge, and the All-Cap 10 system to Lawrence Livermore. We have sold more than 120 tickets for this webinar, and all attendees have been muted by default. We'll be receiving questions through the WebEx chat and also the Google Doc. You can see this slide. I'm going to paste the link that's already actually been pasted there, WebEx chat. And the webinar will have breaks so the speakers can respond to the questions that come in. With that, please, David, Ashley, you give him the screen. Thank you.
Okay, are we ready?
We are ready. Thank you.
All right. So thank you to Ashley and Osni for that kind introduction. Welcome to everyone who has joined us for this webinar. And you get a special bonus today. You get not one, but two speakers. I'll spend about the first 30 minutes talking about proxy apps and benchmarks from a mostly DOE perspective. And then I'll turn the time over to Joe for about 15 minutes, and he'll talk from a vendor perspective. All right. In addition to Joe, who I want to thank for offering his time to be here today, I want to acknowledge a number of co-authors who have been involved in the work that we're going to be presenting today. This is not all my work. In fact, the talk that you're going to see today is an abridged version of a breakout session that was originally presented in the 2020 ECP annual meeting. And the work here involves a number of collaborators who are part of the EC Proxy App team and also colleagues at Oak Ridge National Lab, and I thank them for their contributions. We're trying to address today three main audiences: developers of proxy apps and benchmarks, users of proxy apps and benchmarks, and computing facilities. And we hope that each one of them are going to get some useful information out of this. For the developers, we want to help them understand how to really maximize the benefit that others can get from their proxy apps and benchmarks, and how to develop effective proxy apps and benchmarks. For users, we'd like to teach them about some of the pitfalls that they can avoid and ways that they can find good benchmarks and good proxy apps. And for computing facilities, we also want them to know how they can maximize their use of benchmarks and maximize the quality of the information that they get from their benchmark suites. All right. Now, before we really go any farther, I think the first thing that we need to do is we need to define the terms benchmark and proxy app. So when I think of the term benchmark, this is the definition I came up with, that benchmarks are a sample workload intended to quantify and compare different aspects of system performance. They often get used in purchasing decisions, and they're really a very wide range of benchmarks available. You can see that we have commercial collections like from SPEC. There are open source collections. The DOE has put a number of procurement benchmarks. And a benchmark can range in size from just a few lines of code, for example, the stream benchmark, to using an entire production application to measure the performance of a system, right? But the most important thing about a benchmark is there needs to be a way to rigidly quantify the results and ensure that those results are comparable between systems and between users. Now, a proxy application, on the other hand, is a model for one or more features of some parent application. Because they are models, they typically omit features of their parents. Now, proxy apps, like benchmarks, come in a variety of sizes. For some parent applications, just a single kernel that dominates the performance of the application might be a really good model. If you're trying to represent programming models, or if you're trying to represent communications, then you might need larger bodies of code. The important thing to realize about proxy apps is they are models. And like any model, proxies can be misused and taken beyond their regime of validity. And so, of course, when you take a model beyond its regime of validity, you don't get very good results. And so you need to be cautious about making sure that when you use proxy apps, you stay in that regime of validity. So from these two definitions, I think the thing that we should point out is that many benchmarks are proxy apps. They are models for some workload. On the other hand, proxies are not automatically good benchmarks. They don't have all the features built into them that good benchmarks need. And I've talked a little bit, and I want to emphasize this point, that because proxy apps are models, they're really easy to misuse. Now, some of the blame for this problem lies with developers, because some of us develop proxy apps that we really intend to use only internally. Then we publish them, and before we know it, they're being used for all kinds of things that we never intended. Developers need to be a lot more clear about when they intend their proxies to be benchmarks and what inputs to use. We need better documentation. We need facilities for verification and reproducibility. And of course, the real problem with a lot of the developer efforts is that writing code is fun, but writing documentation is not. And that's where a lot of the problems start. Now, users aren't innocent in all this either. Because proxies are really easy to build and run, it's easy for users to just grab a bunch of them, build them without thinking, run them without thinking, and publish results without really thinking. Proxy apps users, just like the users of any model, they need to be familiar with the caveats and limitations, and they need to describe what they've done. Many proxy apps can be run with various inputs. And so just saying I ran such and such a proxy app is actually not a meaningful statement for many proxy apps. And of course, analyses like sensitivity analysis or making sure that you've got the right performance expectations is also important and something that users don't always think through. All right. Now, if I want to turn a proxy app into a benchmark, there are two things that I absolutely need. I absolutely need a figure of merit, and I absolutely need run rules. That figure of merit is that measure of application throughput performance. If you don't have a figure of merit, then your proxy app is not a benchmark. And your good figures of merit tend to scale with performance. So for example, if your problem runs 2x faster on a problem that's twice as large, that's 4x in the figure of merit. If you run a problem that's 1x as large and it runs 4x faster, that's a 4x increase in the figure of merit. Figuring out a good figure of merit is often tricky. You also need to have run rules. That includes what problem you're going to run, what code version, any scaling constraints, whether or not code modifications are allowed, anything that you need to constrain in running the proxy app as a benchmark. If you don't have those things, you don't have a benchmark. So for developers, you need to provide these things. For users, if you don't see them, that's a clear sign that you may need to look elsewhere if you're trying to do rigorous benchmarking. All right, so let me summarize this little section here with just some best practices across the board. First of all, for developers, write your documentation, make it easy to identify your figure of merit, make it easy to identify your run rules. For users, read the documentation that hopefully the developers wrote. Don't assume that every proxy app is useful as a benchmark. Remember, you've got to find run rules are figure of merit, and DOE system procurements are good places to look. Finally, for computing facilities, try to avoid large input and output files with your benchmarks. They're a real hassle. Make the benchmark suites easy to automate, and try to cover all the aspects of the ecosystem, because there's more to a system than just performance. Or at least there are other parts that enter in that help you get performance. All right, let me pause for a second, see if there are any questions.
Not at this moment.
Okay, then we'll keep on going. So I want to talk a little bit about how one goes about developing a benchmark problem. And I'm going to talk about a proxy app that I've helped develop called Quicksilver. Now, Quicksilver is a proxy app for a production application called Mercury. And it was designed to capture three aspects of Mercury. First of all, that the probability of various nuclear reactions are captured in tables called cross-section tables. That leads to latency-bound lookups. That many, many particles are followed, and they use random numbers to sample those probability distributions. That leads to very branchy and very divergent code, which are not very happy on GPUs. And finally, the particles need to record their results. These are typically done in diagnostic so-called tallies, and accumulating those tallies can lead to potential data races. That's just kind of a very quick overview of what Quicksilver does. Now, we decided that we wanted to use Quicksilver as a benchmark in the Coral 2 procurement. And it turned out to be actually a pretty big challenge to define, to formulate a problem. So let's talk about a couple of the challenges right off. First of all, we needed a benchmark that was going to be equally valid on practically any number of nodes, anywhere between 1 and 10,000 or even more nodes. And any simulation geometry that we thought about that would be a production kind of geometry was going to be very difficult to scale. I've shown here just a typical test problem that we've used in Mercury. It's an annular core research reactor. And you can see that trying to scale that up or scale that down could be a real challenge. There is kind of a sweet spot in scale where that problem operates, but if you're trying to change scale, it's got a very, very challenging problem. Moreover, if you start to decompose that problem, you run into pretty substantial load imbalances, no matter what your scale is. And moreover, the materials that are involved in this problem and the geometry of the problem is part of what gives rise to the whole behavior of the code, the interaction between the materials and the interaction between the geometry. And of course, to make that problem even worse, Quicksilver has simplified physics, and so getting the correct behavior out of the code was even more challenging. So we spent some time struggling with these problems and eventually realized that the only way we were going to be able to solve these problems was to abandon the idea of using anything that resembled a production geometry. But before I do that, let me just focus on some cross sections. Here's another little point that we wanted to address. You can see here I've got cross sections for water and cross sections for uranium. And the elastic scattering, which is that red line on the top of the water plot, that's a really important physical property for the behavior of the simulations. And the dark blue line, the fission probabilities, are very important for uranium. It needs both of those in order to get a good simulation, all right, and to reproduce the kinds of data motion, the kinds of access patterns, the kinds of branching patterns that we see in a realistic code, in a production code. So again, faced with inability to scale the production workloads, we gave up and said, you know what, the only scalable geometry we can think of is a homogeneous single material. That's guaranteed to be scalable, and it's guaranteed to be load balanced. We also came up with some run rules. We said we're going to use a fixed mesh because, of course, you can mesh a single material any way you want to. It doesn't really matter. So we said that they had to use a certain number of mesh elements. And we set a target time range on the wall time per step. that rather than setting a fixed number of particles, we said we want you to target a time interval. And that allowed the benchmark users to scale the number of particles they used depending on how effective their hardware was. And finally, we ended up using made-up materials. As I said, we needed the properties of water and we needed the properties of uranium. Well, if we're going to have a single material, you can't use water or uranium. And so we had to make up a material that had some of the behaviors of both. Now, as one measure of our success in doing this, I just want to show, I'm showing here a graph of the particle energy spectrum for two different problems. The blue line here is the default Quicksilver problem. And the issue we see with that energy spectrum is a very large number of the particles are all in the very high energy groups. That means that the access to the cross-section tables isn't well spread out. We're only seeing the high energy bins. That's not the right access pattern. All right, on the other hand, by working out the details of the material, we were able in our CTS2 benchmark to get that much flatter distribution that you see in the green line. So two morals of this story. One, beware of default problems unless you know they're representative. And two, sometimes the problem that you're looking for to give you the right behavior isn't necessarily the same as a production problem. All right, so with that little story, I guess, we'll pause here and take a look at some best practices for benchmark problems. Again, for developers, when you're putting together your benchmark problems and your benchmark run rules, make sure you address issues of scalability, fidelity, ease of use, and focus on representing the behavior of the program, not necessarily on realistic inputs, because realistic inputs are not necessarily the best way to get realistic behavior. We found it's very important to provide sample inputs and to provide sample FOM data for common hardware. That allows users to make sure they're getting the kinds of results you expect. And finally, be sure to choose a reasonable wall time. Joe will say more about that in his part of the talk. For users, once again, as I already said, don't assume that default problems are good benchmark problems. Oftentimes, defaults are chosen for reasons other than their representativeness. Make sure you understand and make sure you obey the run rules. We've seen numerous instances where people take various run rules or various modeling rules for proxy apps and just ignore them. And their performance results really aren't what was intended. And finally, take time to verify your benchmark performance. Finally, for facilities, make sure you cover the desired rates of system use cases, and Joe will say more about this later as well. Avoid the temptation to ask for every single benchmark you can think of. All right, quick pause for questions.
We are good.
All right.
Everything is clear.
Good. All right. So the next thing I want to talk about is how can you tell if your benchmarks or your proxies are faithful representatives of your actual workload or of your parent codes. And to do that, we in the Proxy App project have been working on a metric called cosine similarity. The idea behind cosine similarity is you take measurements of performance and you express them as vectors in an arbitrary vector space and then take the dot product between them. All right. And the angle of that dot product gives you a metric that is independent of the vector magnitude and gives you sort of a fingerprint of how similar those two vectors are. So you can take a performance vector of a parent and a performance vector of a proxy, compute the angle between them, and if that angle is small, you can judge that they are similar. If that angle is large, you can start to have questions. So I guess what I want to do here is show some of the results that we've obtained as we start to calculate these things. Now, the first problem that you run into when you try and calculate these cosine similarities is modern processors can track hundreds of performance events. And I've just given you here kind of a list of some cache events and some pipeline events that you can track on a modern Xeon processor. And of course, if you really want to know what these things are, you're going to have to get out your secret decoder ring, because the names aren't always exactly clear what they refer to. Now, like I said, you can track hundreds of events, but you can't measure them all at the same time. And if you want to get statistically meaningful values for these things, you may have to run the code several times. That can mean it takes many dozens of runs to get statistically significant values for all of the events. Now, that's clearly very burdensome. And so we really wanted a way to focus in on the counters that were most meaningful. And so to do that, we came up with a selectivity metric. And we ranked these counters by how much variation we saw in them across a set of workloads. And if we didn't see much variation, we said, there's really not much point in collecting this metric, whereas the metrics that were more selective, those were good metrics. And so we focused in for the data that I'm going to show only on the selective metrics. That reduces our workload in collecting these things. All right. And the selectivity calculation, I'm not going to go into those details, but it's similar to principal component analysis. And people have questions, they can send me an email, and we'll get into the details with them. All right. So here I am showing cosine similarity calculations for a number of proxies and parent applications. These were collected on a Broadwell platform. I'm showing the full matrix, even though it's a symmetric matrix, so you can only pay attention to the upper right or the lower left, whichever one you like best. Now, the first thing you notice is that all the applications and all the proxies are perfectly similar to themselves. That's a good check that we get zeros all the way on down the diagonal. You can also see that XMiniMD, which is a proxy for lamps, they have good similarity to each other. Mini QMC and QMCPAC are good and similar. We like that. SW4 Lite and SW4 are pretty similar. SWFFT and Hack are pretty similar. That's good. Pennant and Snap, well, now Pennant is not a proxy app for Snap or vice versa. Those are actually two proxy apps. And you can see they're not similar to each other. So there's a good control that just by putting two things next to each other, we don't get them similar to each other. All right. We can also see that XMiniMD and Lamps really don't have any high degree of similarity to most of the other things in this suite. Same thing for Mini QMC and QMCPAC. They are pretty distinct from almost everything. All right. On the other hand, when you start to look over in the right half of the table, you start to see some areas of this yellow color that says, maybe there isn't that much difference between SWFFT and Hack and SW4. There are some similarities in there. So if we had to cut down the number of benchmarks, maybe that's a place where we could look. All right. So this is kind of just a sanity check that this metric is working as we expect and that we can get useful information out of it. Now, we also did the same set of comparisons on the Skylake platform. And the first thing that we find interesting is that you don't get the same answers on Skylake as you get on Broadwell. We see a lot of the same trends. Again, the diagonal is what we expect with good representativeness of proxies to parents. But we also see that on the Skylake platform, there seems to be a lot more similarity between applications, especially over on the right-hand side of the table. Now, we haven't had time to really dig into what's going on here, but our operating theory is that is probably due to the improved memory performance and the improved memory system on the Skylake platform. And these applications over on the right tend to be kind of more memory dependent. And so that improved memory behavior, we think, is what is making them more similar to each other. All right. If you're interested in only a particular set of groups, particular performance event groups, you can do your cosine similarity using only part of your counters. So here is cosine similarity based only on cache events. And what we see here is that QMCPAC and Mini QMC are somehow different than just about everything else in this little small suite that we're addressing. So if you're looking for something that uses cache in a unique way, Mini QMC and QMC Pack are a good place to go. We can use cosine similarity to find gaps and redundancies in our suites. So for example, you see this big green blob in the middle, that's probably a redundancy. Because there's so much similarity between those proxies to each other, we really wouldn't need all of them in a suite. We could easily drop probably 4 of them without losing very much. Now we can also find gaps. So for example, if you look here in the upper right-hand corner, we've got an area of deep orange and red. Those proxies aren't as well represented. And in particular, if you're trying to use the proxies to model those applications, App 1 and App 2, you can tell that they are the worst representative. So that's a way you can identify a gap in these plots. Finally, your application behavior can vary according to your input choice. So we're looking here at results from Clamor, and we have 6 different inputs, and you can see that we don't have uniform similarity across the board. And this is goes back to our message that you may need to run more than one input. If you had to down select, you can look at this plot and you can say, well, all right, the face in place and the face, they kind of have the lowest sums. If I look across, they look pretty similar to each other, similar patterns. Those two look very similar. On the other hand, if I wanted to pick one that was really kind of unique, this regular grid by faces doesn't really seem to be similar to anything. So maybe if we could only pick 2, we might pick, say, face and regular grid by faces. Probably want to do a more thorough analysis than that just kind of back of the envelope. But this kind of plot can help you answer those kinds of questions. All right, so finally, for benchmark selection and fidelity, quantify the fidelity of your proxy app relative to the actual workload and provide multiple inputs. For users, understand the input sensitivities and choose your benchmarks according to the hardware that you intend to stress. And finally, for computing facilities, consider gaps and redundancies. All right, quick pause for questions.
Yes, David, we have 2 here. One goes some slides back and goes like this. For proxy apps that implement some exact polynomial time algorithm, discerning the figure of merit may not be as difficult as problems that implement some heuristics. Like a number of graph applications could be based on heuristics, which makes formulating the figure of merit challenging. Like traverse the edges per second popularized by the graph 500 may not be relevant for all graph problems. Now the question, do you have a comment about how to deal with such problems where there is essentially no consensus on the formulation of the figure of merit?
Do your best. That's all we can do in research is we propose, we come up with our best ideas, we put them out in the community, and we see how they work. Where there's no consensus, that's where we have to innovate. And no, I don't have the single one true answer. Sorry.
All right. And then there is a question here. The tables that you just showed, these tables are symmetric. Could you compare visually 2 systems by having the data from one in the upper triangular section and the other in the lower one?
I suppose you could. We played around with these visualizations a little bit. We're still playing with these. We tried displaying just triangles, and that didn't look very good to us. But yeah, that's certainly one way you could go about those kinds of system comparisons.
Another question, David. The selective metrics may be platform specific. Do you regenerate the set for each platform?
Yes, we did.
Okay, so another one here, David. Sorry, I missed the first few minutes of your talk. I gathered that you were trying to compare the performance of a benchmarking tool, which you call Proxy, with the real system. Proxy is a model. In order to compare, you have to know how the real system performs. If you already know how the real system performs, why do you need a model?
So often the real code, or at least in some occasions, the real code can't be shared for various reasons, or is too cumbersome to share. You want the model to facilitate easier sharing.
Okay.
It can also be the case that changing the model is easier than changing the full application. And so you can do what-if kinds of studies more easily with the model.
All right. So another question here, David. What is the granularity of the similarity? Wholly proxy application versus wholly parent application, or kernels versus kernels?
So in the data we showed, these are just whole runs. Certainly one could get into collecting that data on a finer granularity and looking at that at a finer granularity. We have not yet had time to do that work.
Okay, David, go ahead, please.
All right. So let me just wrap up here with just a few words about how facilities use benchmarks. And the first point I want to make is that facilities actually use benchmarks for a very wide variety of purposes that might not be immediately obvious. They use it for marketing and program development. The top 500 has been particularly successful there. Now we can argue over whether or not that's a good benchmark, all right, but it's certainly something that has been used to compare and to drive the advancement of computing. And other benchmarks like the Green 500 and HPCG are also used to help drive the advancement and help people who are responsible for funding these systems understand why they're valuable. They're used for application development and readiness. For example, at Oak Ridge, they have their Center for Accelerated Application Readiness, and they use benchmarks in helping to decide which applications to choose, and also for forward-looking kinds of studies. And finally, benchmarks get used for programming model development. For example, at Oak Ridge, they make heavy use of some spec benchmarks, the OpenCL, OpenACC, and OpenMP benchmarks to use along with some other benchmarks to drive compiler development. Hal Finkel at Argonne has also taken some of the DOE proxy apps and introduced them into the LLVM test suite to help make sure that we can compile things that we get the performance we're expecting, and it's just become now a standard part of the LLVM development process. Of course, the most probably visible thing that we do with benchmarks at the facilities is system procurements. And I'll just say here a few words about the Coral 2 procurements and the complexity that was involved in selecting the benchmarks for that procurement. First of all, we had a number of different sites that were involved, both the NNSA sites and the Office of Science, and they have different workloads. And the Office of Science workloads tend to change in time more than the NNSA workloads. And of course, you want to span all the algorithms, all the system software, all the libraries for a system that won't even be built for several years. So that gives you a challenging benchmarking problem. We also had to deal with the problem that we couldn't give vendors every benchmark we could imagine because they only have a few weeks to analyze these things. And finally, we didn't want to cause developers to spend all of their time, all of the time, trying to support the benchmarks as the vendors were trying to analyze them. And like with our question earlier, many of the NNSA apps cannot be publicly shared, and so we had to use proxies for those apps. So a lot of constraints that had to be satisfied. Eventually, what we ended up with was a mixture of production codes and proxy apps in the benchmark suite. So we have some full production apps that we use for scalable science. Many of you will recognize these. And for throughput benchmarks, we use things that tended to be more along the proxy app side of things. And then we added some deep learning and some skeleton and microkernel benchmarks, which I would also consider proxies in many ways. If you want to find these things, you can go look at the Coral 2 benchmark page on the web, and that's a good place to find benchmarks that we've put some pretty significant thought into and are probably pretty well set up in terms of their run rules and their figure of merit. All right, so best practices for benchmarks at facilities. For developers, make your benchmarks easy to run in an automated framework, because when you're running large sets of these things, being able to do it automatically really makes things easier. And carefully consider whether you really want to develop your proxy as a benchmark. It may be the case that using the full application really is the better idea in certain situations. For users, benchmark suites are usually a good indication of what facilities are interested in. And finally, for computing facilities, cover a variety of use cases, avoid large collections, automate, and look for lessons learned that can be transferred to your production codes. And I will do a pause there for questions, and then we'll turn the time over to Joe.
We are good.
All right. Joe, you're up.
Well, hi, everybody. I was asked to provide kind of a vendor view about benchmarks, particularly in HPC procurements. Next slide, please. And next slide. So there's a number of topics that I want to try to address briefly here. First, the challenge of trying to write RFPs, how benchmarks are used in typical RFPs, then discuss a little bit on evaluation metrics, some discussion of projections and estimates, optimization and code modification, and then finish up with some suggestions from benchmarkers in terms of things we'd like you to do and not do. And a special shout out and thanks to Tricia Bao, who helped provide a bunch of material for me. The challenge of writing RFPs, it's difficult. You need to identify what it really is about the system in terms of the characteristics that you're looking at and are interested in, and then ensure that the RFP requirements actually reflect that. You want to eliminate things you don't want and make sure the things you do want are all scored properly. And you want to be able to compare offerings from different vendors. You need to ensure that the document is clear and unambiguous. This is hard to do, but it's important because lack of clarity is going to lead to a bunch of questions. The questions end up wasting time, they end up causing delays. This can even affect installation timing and in the end even affect funding. You want to give the vendors like us a chance to ask some questions, and then you want to be able to share those questions and responses. The vendors will help you shake out problems that are existing in your benchmark set and help identify areas of ambiguity. At the same time, you want to allow for vendor-specific questions that can be kept confidential. Sometimes we'll ask you a question based on some particular advanced technology that we don't want to announce yet. And finally, you have to be aware of the law of unintended consequences. If you set up a procurement in such a way that you're going to require something that is not able to be done in a normal sense, you may end up with the vendors bidding stuff you don't really want in order to achieve that requirement. Next slide, please. There's a number of reasons that people use benchmarks in RFPs. I would argue that the basic aim is to try and measure the proposed machine capabilities in comparison to your proposed workload requirements. In order to do that, you have to understand what it is that you really value and how you're going to score the proposals based on those values, and then provide the smallest set of benchmarks that are necessary to compare the performance. And please keep your expectations of the vendors in proportion to the value of the deal. The time and effort we'll do for a $500 million procurement is different than what we can do for a $1 million procurement. When using benchmarks in RFPs, there's a number of different scenarios that we see. The first, as I've mentioned, is to enable evaluation of the different systems and their capabilities. And sometimes that's just a simple evaluation. Sometimes it's also looking at the vendor's support capabilities and collaboration. They're often used to design and size the system. We want a machine that will be able to run this workload in this time frame. And sometimes they're used as a hurdle in order to thin out the responses and have them focused on people who can better address your system and your needs. Next slide. There's a number of different evaluation methods and metrics that be considered. But I'll say as a vendor, a clearly defined evaluation metric is important so that we can understand where you want to target the performance and what it is that you value. And it's important to understand how the benchmarks are weighted in the overall scoring. Are they a big or a small part of the total final score? And if you're going to determine your entire system size based on HPL results, then let us know that. Beware of benchmark requirements that have nothing to do with the purpose of the machine. Don't stress things that you don't actually need for your workload. and don't avoid things that you do need. And finally, consider appropriate benchmarks to consider things like network congestion. Next slide, please. There's a number of different ways people ask for evaluations. Sometimes it's for us to simply run and report the performance, and that's often used as kind of a barrier of entry. Is this firm particularly able to at least start to address our issues? Often we're asked to run benchmarks under a specified target time. This is often seen in cases like operational weather sites, where they say, we want to know what size of a machine, of what technology you propose, can run this workload in 1 hour or 15 minutes. It's sometimes used to evaluate applications individually and looking at scaling performance up to system sizes. Throughput mixes can be really a useful tool, but at the same time, they can be very tough for us vendors to model, and they require a lot of additional work than individual codes. And so ideally, if you include a throughput, it should displace other things. Weighted metrics have become very popular and useful. An example of this is the Sustained System Performance, or SSP measure. This is where you bundle a mix of applications and kernels, and you weight each one appropriately for your different workload priorities, and then you create a single metric from that mix, often some type of a geomean. This is good because it can allow some variation within a mix at acceptance while still accomplishing the overall performance. And that's especially useful when you're looking at future hardware. Next slide. Projections and estimates are essential if you're looking at any system that's going to include hardware that's not yet available, or if you're looking at system sizes that are beyond what is available to the vendors in their benchmark labs today. Of course, you have to figure out, do the vendors know what they're doing in terms of deciding how to evaluate their projections? You have to look at their prior record. You should ask for an explanation of the methodology, but don't expect the full details. Many of us consider those trade secrets that we don't share. You can think about the relationship you've had with the vendor, and perhaps the most important thing, think about and ask for a full commitment by the vendor to the proposed performance. You can give them a little wiggle room, plus or minus 5%, for example, but expect them to live up to what they are projecting. That will help you get very clear and useful results. You need to decide if you're going to allow processor or interconnect vendors to supply the benchmark results. This can often lead to identical results coming from multiple different system vendors. And you can think about it, if you require a system vendor to run the benchmarks, you get a better assessment of their potential for supporting your work and needs in the future. And if you are going to let processor vendors or others supply the benchmark results, and the system vendors just bundle them in, figure out and decide who's going to estimate the future system performance and who's going to be committed to it. And then finally, when you're looking particularly for estimates and projections, be very careful of applications that use random number generators or iterative solvers. Those can vary from run to run and can make it difficult to do a good projection. Next, please. Optimization and code modifications. Overall, we think it's best to allow optimizations within some guidelines. Quite frankly, most legacy applications won't just scale up efficiently unless they've been adapted to either the current or future hardware. Optimizations allow us to show you the full potential of system hardware, compilers, and libraries, as well as showing us what type of skills the vendor has to help support you in future collaboration. Next. Now I want to switch and talk a little bit about some do's and don'ts, what benchmarkers like and don't like to see in procurements. Next slide. First off, figure out what you really want. Different systems are used for different purposes, and different ways of operating can affect what you desire. Make the benchmark instructions clear. Make sure that different parts don't conflict with one another. And remember that what you have in your own working directory isn't necessarily sufficient for distributing as a benchmark. Supply appropriate validation requirements and make sure they're also clear. And watch the run length. A good benchmark is going to be somewhere between 5 minutes to an hour. Under an hour allows us time to debug, optimize, and figure out the best way to run the application. On the other hand, really tiny benchmarks under 10 seconds are not very helpful at all. And if you end up shortening a run, say your normal production workload takes 6 hours and you're going to cut it down to 1 hour, make sure that you make it an appropriate piece when you do the figure of merit. You may want to skip the initialization portion, for example, in order to get a more useful result. Next, please. Some more things to think about doing. Set an appropriate deadline for when you want to get the results. You have to allow time for the vendors to do the work, and the more complicated the set of benchmarks, the more time that's needed. And if you make the time too short, we'll still respond by your deadline, but the quality of our response will be less. Remember the impact of year-end holidays. Make sure that any penalties around missing targets are clearly defined. That way we can understand and evaluate the risk of the projections and information we're providing. And when it comes time for your acceptance, be pragmatic about meeting targets. If the system hardware was not yet in production at the time we made our initial estimates, you should expect some variation in the final performance. This is where weighted metrics, like the SSP I mentioned earlier, can help in terms of evaluating the overall performance of the machine. Next slide. And then a few things to avoid. Please don't add too many requirements to restrict how benchmarks can be run. Specifying the number of ranks or OpenMP threads, or assuming things about the number of CPUs or cores or accelerators per node can really limit what we're able to do. Unless those are absolutely mandatory requirements for your system for some reason, give us the flexibility to demonstrate the best way to run the application on our proposed architecture, and allow us to use different compilers, MPIs, libraries, etc. Don't ask for a large number of commitments that have no clear purpose. For example, it's easy to ask for tons of MPI tests, but it's hard to understand what they mean, and quite frankly, it's very hard for us to provide them, particularly for future systems. Next, please. Don't expect output to be bit identical to that from another system. Think about the amount of precision you need. Think about the accuracy that you really have. If for some reason you insist you get identical runs giving identical output, say so. That could limit optimizations. For example, different MPI barriers and reductions happen in different sequences depending on the rank count. If you want to have it absolutely identical, we may have to restrict what we can do. And of course, the code has to be written to support this in the first place, and many codes are not. Please don't require huge amounts of output data to be returned. Think about what you're actually able to look at. Think if just the final few steps would be sufficient. If you have tons of data that you need to evaluate, can you provide a tool that post-processes the data so we only have to send you a summary file back? Large data just adds to the time, which cuts down the amount of time we have to do the actual work. Next slide. In conclusion, define your workload first, then design the minimal set of benchmark tests to reflect that workload. Write the RFP benchmark requirements as clearly as you can, and have them tested by others before you release them to vendors. Define a clear evaluation metric to enable comparison across vendors and to help you get the system that you want. And allow its vendors to show what the proposed system can do to help your scientific workloads perform as well and as efficiently as possible. Thanks. Are there any questions?
Yes, Joe, let's go backwards here. I think actually the first, it's a comment, I think. It goes like this: huge +1 to using real apps as procurement benchmarks from a vendor who is more than happy to do projections on 1 million lines of code for Tron legacy codes. I think that was a comment. If the participant would like to elaborate there in the Google Doc. So then going back to slide 33, Joe, the question was, could you give an example of the law of unexpected consequences?
Sure, and it's kind of alluded to on the slide here. We've seen procurements come out where the customer has a set amount of budget. That's very common, and they also said we need to achieve this number on an HPO LINPACK run. The problem was the only way to do that was to distort the configuration of the system to be able to accomplish that goal within that budget. And that came at the expense of the system network and the system storage and I/O capabilities, and it came at the expense of the system being useful for most general science work. It was an excellent design for running LINPACK, but it was not that great for the other activities they wanted to use. And that sort of thing can happen. I'm sure when they set the number, they weren't saying, change the system so the only thing it will ever be useful is LINPACK, but that was the impact of what happened.
Okay, and then there's another one here. Let's see who would like to take this one, Joe or Dave. Can you comment on how we can validate that the numerical results of a proxy application are equivalent to the parent application?
So I'm not sure that's the right question that you should be asking, right? The question in a benchmarking sense is usually a question of, did the benchmarker get the correct result? The question of comparison between a proxy and a parent is more of a fidelity question. And again, that's going to be an art, as with most modeling questions, right? If they're not directly comparable and obviously comparable, then you're going to need to get with the subject matter experts and come up with ways to make those comparisons.
Okay, I don't see any further questions here.
All right, then let me just show just a last slide here.
Sure, go ahead.
So just to kind of wrap it up here, I've taken some of the best practices and some of the suggestions for the various three groups and just put them all in a single slide here. If there's one thing I'll emphasize more than any other, for the developers, write documentation. For the users, read the documentation. And for the computing facilities, you know, all the aspects of the ecosystem are important. And so having benchmarks that and this is kind of what Joe is alluding to, that are not just focused on performance, but are also focused on making sure that your compilers work, your debuggers work, your performance works, your performance tools work. Those are all important things. And I'll just leave the rest of this up here for people to read.
All right, David and Joe, I think that's all we had here in terms of questions. Thank you very much. Ashley, I'd like to announce the next webinar, please.
You should now have control, Osni.
I do have control here, and I'm going to share my screen to announce. First, we'd like to keep improving this series of webinars, so please take a few minutes of your time. This is a link there to SurveyMonkey. Give us feedback so we can, as I said, improve the series. The slides and recording will be available next week at those two sites there. And the next webinar is going to be in about a month, Accelerating Numerical Software Libraries with Multi-Precision Algorithms, and that's going to be presented by Hartwig Gantz from the Karlsruhe Institute of Technology in Germany and Piotr Leszek from the University of Tennessee. The meeting is already there online, so you can sign up for attending it. Thank you all for attending. Thank you, the speakers. Ashley, do you have any final?
No, I was just, oh, sorry, David.
I was going to say thanks for inviting us and thanks for giving us the opportunity to share this material. We hope people find it useful. Ashley?
Thank you. Well, speaking of the material, I had a few people ask me, so I thought I would just advertise this broadly. We will have this video uploaded in the next few days to our ECP YouTube channel. And then once we have it uploaded, you'll get an email with a link to where you can find the video, the presentation, as well as the answers to the Q&A, or to the questions that you asked today. And I think we may have had a couple questions come in right at the very end, so we'll get those in the Q&A doc, and hopefully David and Joe can help get those answered. Thanks again, everyone, and I hope everyone has a wonderful rest of your Wednesday. Have a good day.
Thank you. Thank you, Dave and Joe. It was great to work with you. It's been
our pleasure. Thank you very much.
Sure.
Yes, indeed. Thank you all.